Okay, hey everyone. So here's a video lesson for you to work through, go through. Depending on just the way I do it, some might have questions embedded, some might not. Um, and just to kind of clarify things here. So unit one, that's the unit we're in. Logic, that's the first week. And then video 1C, one corresponds to the unit that we're in, and then C just corresponds to that this is the third video in this unit. Um, so that's how we'll denote them. These videos are meant to supplement and clarify the reading material. So again, remember you should be reading, you should be doing the textbook readings first before you watch any of the videos. So when I make these videos, I'm coming with the mindset that you've already done the reading, not necessarily that you know every little detail about everything that you read, but just so that you have an overview of the topic. Um, and of course, if you ever need to go back, like while you're watching this, go back to the reading if you need to say, oh, what is the truth table again? And then you'll be good to go. So one nice thing about this is you can just pause and go at your own pace. Um, so of course, you're welcome to do that. Here in these videos, I'll typically, uh, again, like I said, clarify the reading material, but I'll also give examples that I think are helpful, especially ones that are similar to some of the more challenging exercises in the writing assignments that I give. So if you're looking for help in the writing assignments, make sure you go through these videos and see similar examples. Okay. So just some clarifications about sort of notation among different sources. So the book uses a certain notation, I use a certain notation, other sources use a certain notation. So I just want to clarify some of that right now. So um, number one, right, the book uses the term statement. Um, I'll say most other sources use the term proposition. Um, and again, this is just to mean a statement that is either true or false. What else? So for propositions, um, oops, the book uses uppercase letters. I will use lowercase letters. Um, PQR. But the reason I do that is because I use uppercase letters for predicates. Um, uh, um, so P of X, Q of X, R of X, etc. for predicates. Oops. So just be aware of that. What else? So numbers. Uh, so the book is kind of centered around the natural numbers, which makes sense for a discrete math course. But just some kind of notation. So natural numbers. Uh, so what is that? So that's just the counting numbers essentially, and the book starts counting from 0. So 0, 1, 2, 3, etc. So there are infinitely many natural numbers. You go as high as you want. Um, And the notation is for sets, which is part of Unit 2, which you'll see next week, is to put the elements of the set or the numbers here in curly brackets. And there's a shorthand notation for the set, so you don't have to always write it like that. It's like the letter N for natural, but you put an extra line on the first vertical line of the N. And then I'll also say that I'll start from 0 as well. Again, the book starts from 0, I start from 0, but just be aware if you use outside sources that sometimes 0 is excluded. Um, so there's actually some debate on what the natural numbers should be, whether they should start at 0 or 1. Um, oops. Some sources exclude 0. So just be aware of that. Integers. No debate on what the integers are. They're just all the whole numbers, so it'll be the natural numbers plus the negative whole numbers. So those are the integers. So the notation for that is the letter Z. I think that's the word for integers in German starts with a Z. That's why it's like that. And that set is the set infinite, kind of in both directions, positive and negative. So, all the way from negative infinity, -3, -2, -1, 0, 1, 2, 3, and on. So it's all positive and negative whole numbers plus 0 as well. Um, and maybe I'll make that kind of explicit. So these are, so from 1 to infinity, that's the positive integers. And from -1 to negative infinity, that's the negative integers. So 0 is neither positive nor negative. Okay, so then just because there are lots of examples with using integers and natural numbers, we'll cover evens, odds, and primes as well. So even numbers, those are just um, the whole numbers that are divisible by 2. So that would be, again, they're infinitely many. So -4, -2, 0 is even, 4, etc. And then the odds. -5, -3. Again, there's infinitely many. I'm just starting at a certain point, but I'm using dot dot dots to denote that it goes on forever. So -105 is also an odd number. Curly brackets. And then the primes. I'll be using those as well. So what are primes? They're just numbers that are only divisible by 1 in themselves. So, and there are, you can, so 2, 3, 5, 7, etc. Those are primes. Negative numbers are also primes, but just for simplicity and just for context, for clarity, like the book, and I'll just use positives for the primes. So when I say primes, I just mean the positive primes. So again, these are the natural numbers, or I should say the positive natural numbers. No, I can say natural numbers. which are divisible by exactly two natural numbers. That's 1 and the number itself. So it's just numbers that can't be broken down into smaller factors. Um, and so, I say exactly two divisors because 1 is not a prime. 1 is divisible by 1 in itself, but 1 is itself. So it only has really one divisor, not two. Um, but primes are, 2, 3, 5, 7, 11, and etc. And a very famous theorem does say that there are infinitely many of these as well, proved by Euclid a long, long time ago. And just as a kind of non-example, so 6 is not prime. Why? Because 6 can be broken down into 2 and 3, two smaller numbers besides 1 in itself. Right, so 6 is 2 times 3. And the number that's not prime is called composite. Okay. So that's kind of it for the just notation, clarification, and all that stuff. Now we'll get into some examples or some concepts, starting with De Morgan's laws. So again, you should have done the readings and found De Morgan's laws in there and reviewed them, but I'll kind of go through a little more in a little more detail. Okay. So first, maybe a definition, which again, you should see in the book, but maybe for completeness, I'll put it here. Two propositions, propositions are logically equivalent. If they have identical columns. Oops. They are truth tables. And it's denoted like this. So it's like an equal sign, but with an extra horizontal bar. And so what's De Morgan's laws? So number 1 is not P or Q is equivalent to not P and not Q. And then number 2 is that not P and Q is equivalent to not P or not Q. So an example for the first one, just written in plain English, right, is could be something like this, a proposition like I don't want soup or salad. That's like I'm saying I want neither of those things. And so if P is the proposition, um, I want soup, and Q is I want salad, then um, one way of saying this is I don't want either of those things. So soup or salad? No. And that would be the left-hand side of 1. So not P or Q, right? Like I don't want soup or salad. But that's equivalent to saying, although you probably wouldn't say this at a restaurant, I don't want soup and I don't want salad, which would be like this. I don't want soup and I don't want salad. In English, it's not literally the same words, but logically they're equivalent. Um, so I'll write it. So I don't want soup and I don't want salad. All right. So logical equivalence is important because it kind of helps us, decode certain things either in the English language or more commonly in programming. Um, well, I guess depending on your line of work. But yeah, De Morgan's laws is just this helpful way to kind of translate between two things that are logically equivalent when you're negating over an or when you're negating over an and. The way I like to think about this is it's kind of like distributing the not symbol, except you have to flip or to and vice versa. So like in the first one, right, I'm kind of can think I'm distributing the not to both, except I have to flip the or to an and. And then for the second one, right, I'm distributing the not to both, but I have to flip the and to an or. Um, that's kind of the quick way to remember those statements. Okay, so that's De Morgan's laws. Uh, we can show also the logical equivalence. Let's do that with the first one. The second one actually is a writing assignment problem. So I'll let you do that one, but just as an example to help you out, we'll do the first one here in the video. So how do we show these are logically equivalent? So show not P or Q is equivalent to not P and not Q. So to do this, we set up a truth table. So we have two atomic propositions, atomic meaning just them by themselves. These are called molecular, right, if they're chaining more atoms together. So if it consists of more than one atomic proposition, it's called molecular. So what are the 4 possibilities when you have 2 propositions? Well, they could both be true, or only P could be true, or only Q could be true, or they could both be false. Okay. And so we want to figure out the truth table column for this statement first and then this statement. And I like to add columns that sort of are intermediate steps to help me out. So before I do not P or Q, let me just do P or Q and then negate that. And there are different ways to do truth tables. You might find sources out there that kind of give you a different way. But yeah, so I'll do sort of P or Q first and then negate it to get the left-hand side. So P or Q is true as long as one of them is true. So yes, both true. One true, and so the only one that's false is when they're both false. So remember, logical or might be different than how you think of it in the English language. usually if you said, I want soup or salad, then you don't have the option of both. But logically speaking, right, having both is true for or, right? So just note that. Um, okay, and then we just negate. So what's the negation of this? Well, just flip every single one. So true becomes false, 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 true. Okay. Oh, and actually, maybe I'll kind of highlight this column a different color to show that it's actually this side. Okay. Now I have to check the other one. So uh, I'll do intermediate steps to kind of help me out. So before I do that whole side, I'll just do not P first and then not Q. So not P, not Q. So I just look at the P column and then not P is the negation. So true, true, false, false becomes false, false, true, true. I go false, false, true, true. And then for not Q, right? It was Q is true, false, true, false. So in those same scenarios, not Q becomes false, true, false, true. And then lastly, I have the right-hand side of De Morgan's law, the first one, not P and not Q. And so for this one, right, the final step. So instead of kind of looking at these and then negating and then doing the conjunction, um, I'll just look at these two and see when they're both true. So remember for and, we need them both to be true. Um, so no, they're not both true. No, they're not both true. No, they're not both true. But here in the final row, not P and not Q are true. And of course, that was because P and Q were both false. So not P is true and not Q is true. And so then we check those two colorful columns. And so since these are identical, that means that they're both true. Or that means that they're equivalent. So that's how we would show two things are logically equivalent. We just compare their truth tables. Okay, so another classic problem you'll come across when you're first introduced to logic, which I think was actually how the textbook introduces the whole chapter, is with a knight and knave problem. So there's these riddles where certain people always tell the truth and certain people always lie, and you're trying to figure out which is which. I think the classic is like there's a fork in the road and two people each say one thing and you're supposed to figure out which way to go. But there's all sorts of variations. And there are some problems in the first writing assignment with these knight and knave problems. So let's do one. But I can't find my example. Okay, sorry about that. So let's do an example with those knights and knaves. So on Logic Island, there are two types of inhabitants. Knights, they always tell the truth. And knaves, they always lie. So your job is to figure out who is who. And again, these are just fun riddles to go through, but the purpose of them is also to kind of reinforce um, the material we've been covering and kind of help you um, kind of decode or figure out ways to solve problems using the tools we get from this course that may not on the surface look like any tools are applicable. So, um, okay. So you meet two inhabitants, call them A and B. Um, and A says, exactly one of us is lying. And B says, at least one of us is telling the truth. So how do we figure out which is which? Um, well, we can kind of encode this as propositions and a truth table and get our answer that way. So hopefully you kind of played around with it during the reading because there were some questions on that. But here we'll have kind of a formal process where you can figure out who is who, or figure out that it's impossible to tell who is who. Um, so let's go through this. So first, what we need to know is we need to know, who's a knight, who's a knave. So we'll go through some propositions. We'll say P is the proposition that A is a knight. Whoops. And Q is going to be that B is a knight. And this is really all we need because then, not P is that A is not a knight, but since Logic Island only has two types of inhabitants, they must be a knave. So not P means or is equivalent to that A is a knave. And similarly for not Q. So, well, if we set up a truth table, then with P and Q, we'll kind of get all possible scenarios, right? So there are four possibilities here, right? Either they're both knights, or A is a knight, B is a knave, or vice versa, or they're both knaves. That's all four. So we can go through those in a truth table. So PQ, just like before. They're both telling the truth, or just P is telling the truth, or just Q is, or they're both knaves. Okay. Now I need to encode their statements using symbolic logic. So A says exactly one of us is lying. Um, so how do we get to that? Maybe I'll kind of write that up. I'll rewrite this over here. Remember what A says. So exactly one of us is lying. Um, well, that means that either uh, A is a knight and B is a knave, or vice versa. We have a symbol for that, right? So it kind of means, um, well, it means, that we'll say it kind of like this. So we want, um, so that means that A is a knave, or uh, B is a knave, but we don't want them both to be knaves, right? So we can say something like, um, they're not both knaves, so not P and not Q. So, oh, whoops, did that wrong. So we don't want them to, this is kind of a convoluted way of saying this, and there's a much simpler way that I want to get to in a second. Um, so this is that A is a knave or B is a knave, and they're not both knaves. But we have a nice way of saying this using exclusive or. So this is just P exclusive or Q. And remember that is exactly, oh, I should say, well, this is logically equivalent to that. But what I meant to say is not P or not Q, just so that it matches um, the, uh, the actual quote, A's actual quote. So we have that one. And then B, what did B say? B said, at least one of us is telling the truth. So that could either mean that A is telling the truth or B is telling the truth, or both, but that's just logical or. Right, so this is just P or Q. Okay, so um, maybe it helps to have some intermediate steps, right? Like not P and not Q. You could also figure out that um, that that's also equivalent to P exclusive or Q, so that we could ignore the knots, but just for as much detail as possible, or kind of a template for how you can approach these problems, we'll do them. We'll do them both. So the intermediate steps here, right? Like not P and not Q. So again, we just kind of flip everything. So P goes true, true, false, false. So not P will go false, false, true, true. And then Q would go, or sorry, not Q would go false, true, false, true. Okay. And so then A's statement, not P or not Q. So exactly one of us is lying. That corresponds to, maybe you can just read it from here, exactly one of us is lying. That's one of these. So same thing here, right? Exactly one of us is lying. So uh, no, yes, yes, no. Okay. And so, oh, maybe I should let me kind of do what I did last time, kind of make different colors. Oops. And so that's what we have for A. And if we look, right, we can kind of see, well, this is what we think A is, a knight, or in this scenario, they're a knight, but in this scenario, they're both telling the truth. So saying exactly one of us is lying is a false statement. And you can't have a knight saying a false statement. So it's definitely not this scenario. They're definitely not both telling the truth. That would be a contradiction. So what's some that are consistent? Well, maybe um, P is a knight and Q is a knave. And so does that work here? Yeah, because then we are sort of saying, oh, this is a scenario where where A is a knight, so A is telling the truth, and they're saying something that's true. Saying exactly one of us is lying is a true statement in this scenario because exactly one of them is lying. So that one could be it. Uh, and then another one that could be it is the bottom one, right? If uh, if they're both lying, then saying exactly one of us is lying is a lie, but liars should lie. So it's consistent. So we're not just looking for all truths, we're looking for sort of a consistency, right? If from these are kind of like the assumptions. So if we're assuming um, A is a knight, in other words, P is true, then they should say something that's true. But if we're assuming that they're a knave, then they should say something that's false, right? But of course, this has to be consistent for both of them, or for both P and Q. So let's do B's statement, which is that at least one of us is telling the truth, or just in symbols, P or Q. And so we know that's true as long as one of them is true. So that's here, here, and here, right? Because we have at least one is true, at least one is true, at least one is true. And then here, no, right? Because not at least one is true. So that's false. Okay. And so we kind of checked that, oh, well, there are only two possible scenarios after A's statement that could be true, the second and fourth rows. And let's just check those. So, well, here, okay, that's good. But here, um, there's supposed to be a knave, but they're saying something that's true, right? Because saying at least one of us is telling the truth is true here, because but knave should lie. So if we're assuming B is a knave, then they should lie. So it's not going to be this one. So let's check this one. Well, uh, here we're assuming B is a knave. And then when they say at least one of us is telling the truth, that's false. But knaves are supposed to say false things. They're liars. So we have this consistency here. So these match. Therefore, we know this is the only possible outcome. If you had two rows that match, then you wouldn't know, right? Because there could be multiple possibilities, but here we know now that they're both knaves. So this means P is false and Q is false. And so they're both knaves. So that's how you could tackle a problem like that. For this small one, you might have just been able to kind of go through the logic in your head and do that, which is a cool exercise to do. Um, but it's nice to have a strategy, a general strategy that works, because then when the problem gets more complicated, your strategy still works. And it's not as convoluted to follow in your head. And so with that, we can do another example. And this is actually the first riddle in the very beginning of the textbook, or the in the beginning of chapter 1 of the textbook. So we'll do that one next. Okay. So um, the oh, let me I don't have the textbook pulled up. Do I have a textbook pulled up? Oh, it's over here. Okay. Another exercise. This is textbook section 1 preview. So hopefully you kind of messed around with this one on your own, but let's try and do it using truth tables, or yeah, truth tables. So they're called trolls now. So let's see what they're saying. So I called them A and B, but now they're going to be called troll 1, troll 2, and troll 3. So um, troll 1 says, if I am a knave, then there are exactly 2 knights here. If I am a knave, then there are exactly 2 knights here. Troll 2 says troll 1 is lying. And troll 3 says either we're all knaves or at least one of us is a knight. Okay. So again, let's kind of encode these into propositions and see what we get. So kind of starting off the same way, right? We just need to know the, troll 1 status. Are they a knight or a knave? So we'll just say P can be troll 1 is a knight. So not P would be that they're a knave. So P is troll 1 is a knight. Q is that troll 2 is a knight. And R, adding an R, troll 3 is a knight. So here, notice the difference. Again, we're getting more complicated. Whoops. We have 3 inhabitants. So we need a third proposition because we want to know the truth values of all of them. So then maybe it would help to kind of put their statements here as well. So troll 1 says, if I am a knave, then there are exactly 2 knights here. So what is that? We'll kind of put it like this, troll 1. Well, if then statement, right, or also called a conditional, also called an implication, right? We have that P arrow Q notation. So that would be if I am a knave. So when troll 1 says I am a knave, that means I'm not a knight. So that's not P. So if not P, in other words, if I am a knave, then there are exactly 2 knights here. And well, if they're not a knight, then exactly 2 knights here means the other 2 are knights. So that would mean that Q and R are both true. Because exactly 2 out of the 3 just means that. So notice I put the parentheses, right? If you don't, this is kind of an ambiguous statement. This could mean not P implies Q and R, or it could mean what we want it to mean, which these are logically different. Not P implies parentheses Q and R. So we want those parentheses there. Okay, and troll 2. Troll 1 is lying. Okay, that's more straightforward than the last one. Troll 1 is lying just means that they're not a knight, so that's just not P. And then troll 3. Says either we're all knaves or at least one of us is a knight. So there's a kind of an overarching logical or here. So either we're all knaves. So all what is all knaves? That just means they're all false. So that either means not P and not Q and not R, right? All of them are lying. Um, or maybe I'll kind of highlight this. Oops. Or, that's this or, at least one of us is a knight. So at least one of us is a knight means that either P is a knight or Q is a knight or, sorry, troll 1 is a knight or troll 2 is a knight or troll 3 is a knight. In other words, that means P, Q, or R. So P or Q or R. And notice when you have more than one conjunction together or more than one disjunction, ands, ors, you don't need extra parentheses, right? So like this is not ambiguous. This just means all of these are true, or in other words, they're all not true. I mean, and this one means at least one is true, just like with an or with two, right? So for this to be true, you just need at least one of them to be true, which is exactly what troll 3 is saying there. Okay, but there's something funny about troll 3's statement, which we'll get to when we get to the truth tables. So truth tables become a little bit bigger, or a lot bigger, when we have more extra propositions, or more than two, I should say. So we have a P, Q, and R. So those are going to be our first three columns. So P, Q, and R. And so when it's just P and Q, when there are just two atomic propositions, there are four possible outcomes, right? True, 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 false, false, true, false, false. But for three, there are eight. And it might be hard to keep track of, you don't want to repeat cases or repeat scenarios. So kind of the cheating way of doing it, or the quick way of doing it without thinking, is to just go by column. So for P, you do four trues, then four falses. So true, 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 false, 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 false. And then for Q, you do two at a time. So two trues, two falses, two trues, two falses. So you do two at a time. T, T, F, F, T, T, F, F. And then for the last one, you do alternating one at a time. True, false, true, false, true, false, true, false. So true, false, true, false. And this guarantees you'll get all eight possible scenarios. Right, so just to kind of ground ourselves, right? This first scenario, the first, here we're assuming that they're all knights. And then just take another one. Here we're assuming that troll 1 and troll 3 are knaves, but troll 2 is a knight. Okay. So what propositions do we need? Well, for one, right, we need this. And so I'm going to break this down into two intermediate steps here. So I'll use both of those, not P, and then Q and R, and then we'll do the implication. So Um, so not, whoa, not P, and then Q and R, and then the actual implication. So that would be not P implies Q and R. Just make sure we have that right. Yeah. So in these 8 scenarios, right, for P, for not P to be true, that's just exactly when P is false. So we just kind of look the P column and negate it. So it becomes 4 falses followed by 4 trues. And then Q and R. So now we just have to look at these 2 columns and see when are they both true. So they're both true only in 2 scenarios, this one and this one. So we have both true, no, 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 yes. Okay. And then the implication itself. So remember, implications or if-then statements or conditionals are true when, well, they're true 3 out of 4 times, essentially. Um, either when the hypothesis is false, so when this is false, or when the conclusion is true. So that's every case except when this is true and this is false. So we're just trying to avoid that one. And again, there's an earlier video that kind of gives you the more foundational introduction to implications, and it's in the book as well. Okay, so make sure you're looking at those first. So now we're looking at the previous 2 columns. False to true, that's okay. False to false, that's okay, right? Again, so if the hypothesis is false, we're okay. So these are all okay. Don't even have to look at the conclusion. And now true implies true, that's okay. But these 3, right, we have a true hypothesis followed by a false conclusion. Those are not okay. So those are all false. So, oh, and I forgot to color code. So that's the actual, like, what troll 1 is saying. And then troll 2 is not P. So that's, remember, they're just saying that troll 1 is lying. We already have a column for that, but I'm going to repeat it anyways, just for, I don't know, because I feel like it. So not P, again, that's just a repeat of, we already have that column because we used it as an intermediate step. You don't have to do this, but I like to keep myself organized in this way. Okay. And then the last statement, okay, well, what is the last statement? This is basically saying we're all lying, or at least one of us is telling the truth. Is that ever going to be false? Think about it. So I'll write it. What color do I want to use? It's purple. So I'm not going to do intermediate steps for this one. So we have not P and not Q and not R, or P or Q or R. So this is always true, actually. And if you think about it, right, and if you're not comfortable with that, go through the truth table and figure it out for yourself. Um, right, but they're um, they're negations of each other. And actually, if you use De Morgan's law on the left-hand side, you can kind of we only showed it for two propositions, but you can do it for three. You kind of can I said I use the analogy of distributing the negation, but we can sort of factor out the negation, but then we'd have to flip the the logical operators. So that would be the exact negation of this, right? Either we're all lying or at least one of us is telling the truth. That's always going to be true. So true. Okay. And so now we have a completed truth table. And so what we have left to do is to look at PQR, that triplet, and see when it matches the three colorful uh, columns or those triplets, because that's what they're saying. So, right, this is sort of our assumption. We're here in this scenario, right, in this universe, kind of there are eight universes here. We're in the multiverse. In this universe, they're all knights. But if they're all knights, then these are the truth values of what they're saying. But they don't match, right? They're not all knights, right? So because not P is false, so you can't have P be a knight um, and Q be a knight because uh, Troll 2, which is associated with Q, Troll 1 is lying. Well, if they're telling the truth, then Troll 1 has to be a liar. But if Troll 1 is not a liar, then that's a contradiction, right? So we just need these to match. So let's try and look down the line, see where they match. So not the first row, not the second row. Third row looks good. And so we might just be like, oh, well, that's our answer. Um, but we want to be careful because um, there could be multiple scenarios that are valid, and so you might not know, you might not be able to determine with certainty who's a knight and who's a knave. So we have to make sure that none of the other ones are consistent. So, um, right, true, false, false doesn't match. True, false, true. Um, this one doesn't match, doesn't match, doesn't match, doesn't match. So, okay, now we can say for certain though that um, that the third universe is the true one, where Troll 1 and 3 are both knights, and Troll 2 is a knave. So Trolls 1 and 3 are knights, and Troll 2 is a knave. So let's just kind of double check their statements, what they said against our answer, and make sure. So Trolls 1 and 3 are supposed to be telling the truth, and Troll 2 is supposed to be a liar. So Troll 1, if Troll 1 is a knight, then saying this, if I am a knave, then there are exactly two knights here. Well, their hypothesis, if I am a knave, is false because they're a knight. And remember, if we have a false hypothesis, the implication overall is always true. So that's good. That means that Troll 1 is telling the truth and they're a knight. Um, and then Troll 2 says that Troll 1 is lying. Well, that's a lie because Troll 1 is a knight. So that means Troll 2 must be a knave. And is that what we concluded? Yes. And then, well, Troll 3 has to be a knight because what they said is always truthful. So they have to be a knight. In a truth table, or I should say in a proposition, if It's always true, like this. There's a special name for that. It's called a tautology, Tautology. So if you come across that term, that's just what it is. Okay, what else do we got? So those are the two logic island examples I'm going to cover. Next, I want to make some more clarifications about quantifiers, just the notation of them. So again, you should know what a quantifier is from the reading, or at least have a basic idea. And I'll clarify some things here, and then we'll do some examples.